Hello everyone, welcome to my video on Principal Component Analysis or PCA in short. In the world of computer science, bioinformatics and in many other places, PCA is the most widely used algorithm there is. Unfortunately, when we use PCA, we use it like a magic box. So we just simply use some library, we apply PCA on some data and it magically reduces the dimensionality of our dataset. But in this video, we are going to make sure that we understand everything there is to understand about PCA, including its geometrical interpretation, how to derive the principal component axis, and many other things. So let's dive in. So first of all, we see that there is a stretch of data points right here. You can think of each data point as a two-dimensional sample. So there are many samples right here, and they all stretch in a certain direction. You can clearly see that. This is the x-axis and this is the y-axis. Now we can actually create a new axis right here, right? So it's not the x-axis, it's not the y-axis, but it's a different axis, but it's the axis in which we can see that the samples or the points are spreading the most. Now, obviously we can take the projection or the perpendicular point towards these axes from the sample points. And if we actually draw those projections, the points will look something like this. So we can actually think of this whole scenario like this. So if we sort of transform these points onto this new axis right here, their new coordinates will look something like this, something like the deep blue points, right? The nice deep blue points. So this is going to be called PC1 or principal component axis 1. So PC1 is the direction with the highest spread or the highest variance of the data points on our space. Now, PC1 is good, but there are other things as well. We can also draw another axis right here. You know that the x and the y-axis are actually perpendicular to each other. That means they are 90 degrees. So the other axis we can also draw in perpendicular to the PC1 axis. So this is that axis. Now we can also take the projection of the points onto this axis and they will look something like this. But as you can clearly see that they don't have as much variance as we had in the PC1 projection, right? Which we saw in the previous slide. So this axis is called the PC2 axis, which has lower variance compared to the PC1, and it is also the orthogonal to PC1. Okay, so this is for the 2D case. Now you can think of the whole scenario as a brand new coordinate system. So what do I mean by that? So let's actually see this in detail. So the x-axis can be represented by 1, 0. So this is a unit vector because the squared sum of these elements is 1. This is also a unit vector. The squared sum is 1, and they are also perpendicular to each other. Here, assume that PC1 is this vector and PC2 is this vector. Actually, it makes sense. You can see that this is the direction of this vector right here. So it makes sense. Now, you can see that this is also a unit vector because the squared sum is 1. This is the same, and they are also perpendicular to each other. So you can actually transform your point into PC1 and PC2. So basically, you have changed your coordinate system. So if the original values of your samples were x and y, your new values will be PC1 projections and PC2 projections. So it's a new coordinate system. Now, this is only the 2D case. So what about 5D, 6D, etc.? Because obviously in your dataset, you can have samples with hundreds of features, right? So suppose your points are 5D. In that case, you are going to have 5 PC axes, right? Because here you have 2 PC axes for 2D. And each of your PC here is represented by 2 elements, 2 element vector. But for 5D case, those will be 5D. So here you will have 5 elements, basically. And this is obviously a new alternative coordinate system, as I mentioned before, and your axes will be ranked by their projected variance. So PC1 has the highest variance, PC2 has the lowest variance right here. But for 5 PC axes, PC1 will have the highest, PC2 second highest, PC3 third highest, and so on and so forth. So how do we measure the variance, right? We are talking about variance a lot. So how do we measure the variance of a single feature? So suppose this is a single feature and you have these samples. I mean, you have like 5 samples right here. And these are the values of feature xi for those samples. The mean here is 11. Now you can calculate xi minus x bar whole square for each case, and you can sum them up, which is 10 right here. Then you can actually calculate this formula. this is the formula for variance calculation of a single feature. So summation of xi minus x by whole square is 10 right here. And n minus 1 is basically 5 minus 1 equal to 4. So the variance is 2.5. So this is how we calculate the variance. So you can think of a dataset with 1000 samples having a feature, say, length. So there can be different lengths like 5, 10, 11, I don't know. That means the feature length will actually have 1000 values across the whole dataset. That means this column right here, this xi column here this will be length. So length will have 1000 values, and you can obviously use this formula to calculate the variance of that length. But that is only for one feature. How about covariance between two features? Because obviously in your dataset there can be hundreds of features. So obviously you will want to understand the covariance or the relationship between every pair of features. So how do you do that? Now, first of all, I want to mention that this variance and covariance, they are very important to calculate the covariance matrix of a dataset. Now, why do we care about the covariance matrix? Because that is the basis of obtaining the principal component axis. So that is why I am discussing these things first to give you some prior knowledge. So here we have two features, xi and yi, and these are their values. And we have obviously 5 samples. These are 5 samples. We can calculate the mean of x and mean of y. And we can get these two columns as well, which are xi minus x bar, which is the mean of x, and yi minus y bar, which is the mean of y, which is very nice. Now, we can also get the product of xi minus x bar and yi minus y bar. For example, minus 4 into minus 2.6 is equal to 10.4, which is again very nice. So why do we calculate all of these things? So if we sum these things up, it is 28. I also want to mention that. So why are we calculating these things? Because this is the formula for the covariance calculation between feature xi and feature yi. So you have to get the summation of these two products, which is 28 right here, and we need to divide it by n minus 1, which is going to be 7. So this is the result for the covariance between xi and yi. But the question is, what does covariance actually represent? So if you have a high positive covariance, that means when one feature increases, the other also tends to increase, and when one feature decreases, the other also tends to decrease. If you have a negative covariance, it's the opposite. When one increases, the other tends to decrease. But if you have a zero or near zero covariance or a very small covariance, that means they don't really have any correlation, okay, in their variation. So that is basically the significance of covariance between two features. Now that we know variance and covariance, we can finally talk about covariance matrix. But before that, one more thing I have to mention is the symmetric matrix. So this is one property which we are going to use for Eigen decomposition, which is the basis for getting the principal components. Okay, so let's dive in. So first of all, this is a symmetric matrix because here Aij equal to Aji. What do I mean by that? So you can see that this value 1 is in row 2 and column 1. Row 1 and column 2 also has a value of 1. Similarly, row 3 and column 1 has a value of minus 2. Row 1 and column 3 also has a value of minus 2. So they are all equal. They are all sort of mirrored. So this is a symmetric matrix. So if you transpose a symmetric matrix, you are going to get back the same matrix. So transposition means you are making the rows as the column. So this row has become the column of this matrix. Second row became second column, and so on and so forth. But most matrices are not symmetric. For example, this is an example of a non-symmetric matrix. So this row right here became this column. This row right here became the second column, and so on and so forth. And it is not equal to B. One more thing, for a matrix to be symmetric, it needs to be square matrix. That means the number of rows and number of columns need to be the same. So here you have 3 rows and 3 columns. Otherwise, it will never be symmetric. So now finally, we move on to the covariance matrix, which is the basis for the PCA decomposition. So this is our data set. Suppose we have data set where we have S1 to S4, 4 samples, and we have 3 features F1 to F3. So the first step is to actually get the mean for each feature column. So new 1 is the mean for feature 1 column. New 2 is the mean for feature 2 column, and so on and so forth. So then we have to mean center this dataset matrix. How do we do that? We subtract this new 1 from every value of feature F1. So suppose feature F1, the first element of feature F1, we subtract new 1 from that. The second element of feature F1, we subtract new 1 from that, and so on and so forth. We do the exact same thing for F2. We subtract new 2 or the mean from each value of feature F2, and same thing for F3. Next thing is to use this A bar to do a matrix multiplication we multiply A bar transpose and A bar. Now understand that the rows of A bar transpose are the feature columns, or the feature, I mean these columns basically, the features, and in A bar, they are the columns. So if we do the matrix multiplication, we are going to get something like this: F1, 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 F2, F1, F3, and so on and so forth. If you look at this matrix closely, this is a symmetric matrix. Why? You can actually check. So row 2 and column 1 has F2, F1. Row 1 and column 2 has F1, F2. So F1, F2 is the same as F2, F1. So it's a square matrix, it's a symmetric matrix. That is the important thing. But just one more step left. So we need to divide all the elements of this matrix by n minus 1 basically. So I think there's a mistake here. You need to divide all elements by not 1 by n minus 1, rather by n minus 1. I mean, I meant n minus 1 here. Okay. So here you can see that there are 4 samples right here. So you need to divide all the elements by 3, right? Not 1 by 3, by 3. And thus you are going to get the covariance matrix. Now, you may be wondering, why is this the covariance matrix? It's because the diagonals calculate the variance for each individual feature, and the off-diagonal elements calculate the covariance between each possible feature pair. So you may be wondering, why is that? Because you can see we actually subtracted the mean, like we'd have to do in the variance or covariance calculation. And for the whole square, for the multiplication and covariance case, we actually do this multiplication. And we also divide by n minus 1 right here. So it is indeed the covariance matrix. So what does covariance matrix represent? It represents all pairwise covariances between features in your dataset. Now, let's talk about how to find directions of highest variance. So this is basically what we wanted to do so far. We have a dataset, we have all the points from our dataset, and we want to look at the directions with high variances, right? So this is, I think, very clear. Okay, so first of all, this is our covariance matrix C, which is of shape M into M, and this is a vector V, which has a shape of M. This is a scalar value or a constant basically. You can think of it as 5, 6, or maybe 0.5, some value, scalar value, and V is this vector, the same vector. Now this is very strange because you are multiplying this vector by a matrix, and it is actually equal to just multiplying the vector by a scalar value. So this has a special name, this property. So this is the eigenvector of the covariance matrix, and this is the eigenvalue for the covariance matrix. Let me actually illustrate why this is so special. So first of all, you can actually see this picture right here. So you have this vector V, which is 1, 0. If you multiply these by this matrix C, so I'm just taking a random matrix C here. It has nothing to do with covariance. So if you multiply C and V, you are going to get 2, 1. You can see that the vector actually has shifted from its original direction. That means if you multiply this vector by some scalar value, it will not be equal to this value, because when you multiply this by a scalar value, it will either shrink or it will expand. So multiplying a vector by a scalar value only shrinks or expands it. It doesn't change direction. So this is not an eigenvector of C. But let's look at this scenario. So we have 1, 1. We multiplied it by the same matrix. You can see that it has actually expanded in the exact same direction, and it has become 3, 3. That means this is equivalent to multiplying this vector by a value of lambda equal to 3. That means this is an eigenvector and this 3 is an eigenvalue. This is the interesting thing. But it actually represents something very, very interesting. So what is that? Can you think of it? So basically, the covariance matrix C has a lot of variance in this direction of V. This is what we are looking at, right? This is what we are looking for. We are looking for directions where the data set has a lot of variance. And so in this case, 1, 1 is that PC. Maybe it's PC1, right? Maybe it's PC1 for covariance matrix C. Obviously, there is more things. I mean, obviously you saw that there can be more than one eigenvector or there can be more than one eigenvector or one PC, right? For example, for 5-dimensional data set, for 5D features, for 5 features, there can be 5 principal components. So what happens then? So this equation actually allows us to find multiple eigenvectors and multiple eigenvalues. And this is the thing. If you have an M into N covariance matrix, you can have maximum M eigenvector value pairs, right? But it's maximum because you can even have less than M, right? So some of the eigenvalues can be 0 as well. So those are actually not important. I mean, the principal component axis will be there, but they won't have any importance or any variance. That is why the eigenvalue is 0. Okay, so I think you have now an understanding about where the PCs come from, because PCs are nothing but eigenvectors of covariance matrix, because those are the places where the covariance matrix shows its variance and shifts the corresponding vector such that it spans or it compresses, basically. So let's look at the concept of orthogonal matrix before we actually see how we derive those eigenvectors, right? Because that's important for the formula. So this is an orthogonal matrix. If you multiply orthogonal matrix with its transpose, we are going to get back an identity matrix like this, where 1 is all over the diagonal and 0 is in all the other places. So basically QTQ and QQT is equal to identity matrix, but I know that some of you are thinking that hey, if we multiply a matrix by its inverse, then we should be able to get I. But what's happening here? So in case of orthogonal matrices, Q inverse 1 is equal to QT. Right? And there is one more other important property. You can see this vector clearly, that each row is actually perpendicular or orthogonal to all other rows. Because if you multiply this vector right here in the first row by the vector in the second row, it will be 0. Okay. Similarly, if you multiply this row with this row, the dot product, it will again be 0. So they are all perpendicular 90 degree with each other. And it's same for each column vector as well. For those of you who want to see what orthogonal vectors look like, it looks like this. So you have x equal to 3, 2 maybe, and you have y equal to minus 2, 3. They are both in 90 degrees in perpendicular. And if you do a dot product of them, it will be 0, right? So your x-axis, y-axis, they are also orthogonal vectors. They are also perpendicular to each other. Now that we know orthogonal matrix, we know covariance, we know eigenvector, eigenvalue, we can now see how we can obtain the PC axis using eigen decomposition. So first of all, let's assume that C is our covariance matrix with m into m size. That means we have m features. So we are going to get v1 to vm eigenvectors and corresponding eigenvalues lambda1 to lambda m. Now we can actually arrange them into these two nice matrices. So the Q matrix, it has all the eigenvectors or the PC axis in its columns, and this lambda matrix, it has all the eigenvalues in its diagonals. Now these values are arranged in a specific way. Lambda 1 is actually bigger than lambda 2, it's bigger than lambda 3, and so on and so forth. That means V1 actually has the highest variance projection, V2 has the second highest, and so on and so forth. So this equation we already saw where we talked about CV equal to lambda V. Now obviously there are m vectors right here, m eigenvectors, so I have written m here. So we can replace this by Q, right, because Q has everything. So this is what it looks like if we replace this V by Q and this lambda by the lambda matrix itself. So we can multiply these by Q transpose on both sides. There is no harm done here. If we do that, understand that you previously saw that Q is actually an orthogonal matrix. Why? Because these are PC axes, right? And you know that each PC axis is actually perpendicular to each other because they form a coordinate system. That means Q is an orthogonal matrix, and so Q transpose is what? It's an identity matrix I, right? That means Q transpose will actually go away. It will be I, and C and I mean any matrix multiplied by the identity matrix is just that matrix, right? So you have C equal to Q, and then we have the lambda matrix and then Q transpose. So this is what eigen decomposition is. So if you calculate your covariance matrix and give this to a library, to any library for eigen decomposition, it will give you back these three things. Okay, and so you can simply take the columns of Q as your principal component axis vectors, and you can take the diagonal values of these lambda matrix right here as the eigenvalues. But there is one thing, you may also want to know how exactly do we get Q, lambda, and Qt, right? You may also want to know how to do this decomposition by hand without using any library. What is the intuition? So I have made a separate video on eigen decomposition, which the link of which I will provide in the description. So feel free to check that out for seeing the procedure of exactly how eigen decomposition is done, right? Now, I could have discussed it in this tutorial, but it's going to make this tutorial too big, and that's not really the goal of this tutorial, to show how the eigen decomposition is done, right? That's why I'm leaving it here. Now, you have all your pieces. Now, how do you select your top pieces, right? How do you select your top principal components? Because there will be some principal component axis where there is very little variance, so you don't really need to keep those. So how do you do that? So let's see through an example. Assume you have a dataset with 25 features. So obviously we'll have 25 PC axes after you do the eigen decomposition. And you what you actually care about is how many principal component axes do you need so that most of the variance in your dataset is well explained remains, right? So we need to have a formula to see the dataset variance explained by the top n PC axes, or for this example, let's say we are taking top 2 PC axes. So you can actually get this through this formula. So obviously for PC1 and PC2, you know the lambda1 and lambda2, which are the eigenvalues. Your Eigen decomposition will give you those. Now you can square those up and add those things, lambda1 square plus lambda2 square, and you can add all the 25 lambda squares, right? Lambda1 square, lambda2 square, lambda3 square up to lambda 25 square, and you can divide, right? So suppose this value is say 0.8 or 80%. That means the top 2 PC axes explain 80% variance of your dataset, right? Similarly, for top 3, you are going to add lambda1 square, lambda2 square, and lambda3 square in the numerator. Okay. So suppose you want at least 95% of your dataset variance to be explained by your top PC axis. So you can use this above formula for top 1, top 2, top 3, and so on and so forth. And say you find top 5 PC axis. So for top 5 PC axes, for the very first time, your variance actually exceeds 95%. Then you just can move forward with the top 5 PC axes. So that's how you actually choose the top PCs. Okay. So now that you have chosen your top PCs, you would want to reduce the dimensionality of your dataset using these top PCs. So how exactly are you going to do that? So let's actually understand this geometrically first. So you have this point right here, a 2D sample point. So how do you get the value of the sample point on this particular PC axis? The answer is you take the projection. So you take the projection, and this blue line right here, the deep blue line, this blue line right here is going to represent the value of this particular point on this PC axis. So what is this blue line actually? It is nothing but a dot product between the PC axis vector and the sample vector itself, right? So that is the thing. There's nothing else. So now that you understand how you can actually get the PC projection of any sample on a particular PC by doing the dot product, you can also know how you can project the entire dataset on the top PCs only. So let's see how it does. Let's see how it happens. So suppose your dataset has 100 samples and each sample has 25 features. So your dataset matrix is of shape 100 cross 25. And you decided to use the top 5 PC axes, which explains, say, 96% of your data variance. And you can obviously see that using those eigenvalues, right, which I just showed you. Now, how do you actually turn this 100 sample matrix, which is 100 into 25, into 100 into 5 using the top 5 PC axes? Very simple. You do this multiplication. You take the dataset D, 100 samples are the rows and 25 features. You matrix multiply it with the Q reduced matrix. So what is the Q reduced? So we know the Q matrix, right? Q matrix had the eigenvectors or all the PC axes. Q reduced will only have the top 5, right? So the first column is the PC1, the second column is the PC2, and the fifth column is the PC5. If you multiply these two things, you are going to get back this matrix of shape 100 into 5, which is the DR or dataset reduced. Okay, so this is what you have been looking for so far, and the truth is, when you sort of like do a one-line command or things like that, this is what they do. They derive those PCs and they do this projection, right, onto the narrower feature space. So this is how the dimensionality reduction is done using PCA. Now that we know that, one final thing I want to mention is the 2D PCA plot, which is very famously used everywhere. So what's happening here? So suppose this is your dataset, and the dataset comes from 3 classes: Africa, East Asia, and Europe. Those are the 3 classes. And maybe each data point or each sample has maybe 100 features. Now, obviously, you cannot actually plot a 100-dimensional plot because we cannot even visualize beyond 3D as humans, right? And ideally, we visualize well in 2D. So what you can do is you can derive the top 2 PCs, PC1 and PC2, and you can take the projection of your dataset samples onto PC1 and PC2. And then you can color the points according to their classes, and you can visualize if they form some clusters or there is some outlier or something like that. So that is all about PCA, my friends. Hopefully you like the video. If you like it, please feel free to subscribe and share, and feel free to donate to our channel to the link given in the description. Thank you very much.